Hello, welcome back to Guidancee education channel. In this video, we are going to discuss lenses part 2, lens maker's formula. We are also going to derive the formula. Lens maker's job is to design lenses of desired focal length and suitable material. Such lenses are used for various purposes and in various instruments like microscopes, telescopes, etc. The most common application is the making of spectacles. The lens maker's formula connects focal length, radii of curvature and refractive index of the material of the lens. This formula helps them to design the required lens. Before we proceed into the details of the video, please watch the video completely so that you understand all points. And if you think the video is useful, like the video, share the video with your friends so that they also may be benefited. And subscribe to my channel. Please leave your comments in the comment box below. That will be a great motivation for me. Thank you very much. Now, let us proceed. I have made a representation of a biconvex lens here. I have also written the details of the diagram and also derivation in advance so that we can save some time. The lens is placed in medium of air. The lens is made of glass. So, the external medium air is a rarer medium and its refractive index is equal to N1. The refractive index of the medium of lens is N2. N1 is less than N2. O is a point object and it forms an image at I. In order to understand the image formation, let us consider the two surfaces of the lens SAT and SBT. Let us first consider the surface SAT, which we marked as surface 1. A ray of light starts from O and strikes the surface 1 at point A. If surface 2 were not present there, then this refracted ray would pass on along this line and strike this point. From O, another ray starts and passes through the radii of curvatures and optical center and meets the refracted ray at point I1 where real image is formed. So, if only surface 1 was present, the image would have been here. But the medium of the lens is discontinuous because it is restricted by the second surface SBT. So, as the light reaches B, it undergoes further refraction. In order to understand that, let us consider what happens at the surface 2. I1 functions as a virtual object for surface 2 and after refraction an image is formed at I. So, in order to understand the formation of image at I, we have to consider refraction at surface 1 and refraction at surface 2. The image I is the sum total of refraction at surface 1 and surface 2. Let us proceed to understand this. For thin lenses and for small apertures, C1 is equal to P1C1. Because the lens is very thin, this small distance can be neglected and that is the distance R1, radius of curvature for surface 1. Point is marked as C1. Similarly, C2 is equal to P2C2 and that is equal to the distance of the center of curvature for surface 2, which is marked as R2. Again, CI1 is the distance of the image for surface 1 and that is equal to P1I1. In all these cases, we are neglecting this small distance because the lens is very thin and it can be taken as V1, distance of the first image. CO is equal to P1O and that is equal to the distance of the object is represented as U. Let us consider Ci1 again. From the diagram, Ci1 is equal to distance of the object for surface 2. Therefore, it is marked as U. But in this expression, we have Ci1 is equal to V1. So, Ci1 is equal to V1. Ci1 is equal to U. So, we can write this U is equal to V1. That is, this distance can be taken as V1 for surface 2. Ci is the distance of the image for surface 2. That is equal to P2I. And that is equal to V. Now, this we have taken for surface 1 and this we have taken for surface 2. For refraction through single surface, and when the ray is passing from rarer to denser, the relation is given by N1 by negative U plus N2 by V is equal to N2 minus N1 by R1. Similarly, for the second surface, refraction is from denser to rarer. So, the expression is negative N2 by U plus N1 by V is equal to N1 minus N2 by R2. For this case, this is for this case. We want this expression to be similar to this expression. So, we just change it, and we also know that this U is equal to V1, this portion. So, we write it as negative N2 by V1 plus N1 by V is equal to N2 minus N1 by negative R2. We have inverted these two, so we add a negative here. Now, as we have already said, the final image I is the sum of these two expressions. So, we do that, we add up these two. When we add up, in the first equation, N2 by V is positive, in the second it is negative. So, they get cancelled. What remains is N1 by negative U plus N1 by V. What about the right hand side? The numerator is the same. So, we can take this out and keep it as common. So, N2 minus N1 is taken out and kept as common. And then multiply that by 1 by R1 minus 1 by R2. This quantity is common. N1 is common on the left hand side. So, we write it as N1 into 1 by negative U plus 1 by V is equal to N2 minus N1 into 1 by R1 minus 1 by R2. Let us bring this quantity over to the right hand side. So, the equation becomes 1 by negative U plus 1 by V is equal to N2 minus N1 by N1, this N1, into 1 by R1 minus R2. On further simplification, it becomes 1 by negative U plus 1 by V is equal to N2 by N1 minus N1 by N1. N1 by N1 will become 1. Let it be. Let us continue. Into 1 by R1 minus 1 by R2. This quantity is positive and this quantity is negative. So, we just write it the other way. 1 by V minus 1 by U is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. 1 by V minus 1 by U is equal to N minus 1, because N2 by N1 is the refractive index of the second medium, that is lens. So, here N stands for refractive index of lens. We have allotted N2 here, but from this expression it is refractive index of lens minus 1 into 1 by R1 minus 1 by R2. Now, if the object is at infinity, what happens? The image will be at the focal point. V becomes equal to focal length. F is equal to focal length here. So the equation becomes 1 by f instead of v, because v is equal to f, minus 1 by infinity because the object is at infinity, is equal to n minus 1 into 1 by r1 minus 1 by r2. 1 by infinity is equal to 0, so we just omit that. So the equation becomes 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. What are these quantities? F is the focal length of the lens that is used. N is the refractive index of the lens. R1 and R2 are the radius of curvatures of the two sides. This expression is the lens maker's formula. So we have derived lens maker's equation. Let us mark this as equation 2 and this equation as 1. Equation 1 can be written like this. Negative 1 by u plus 1 by v is equal to n2 by n1 becomes n, that is refractive index of the lens. So n minus 1, n1 by n1 becomes 1 into 1 by r1 minus 1 by r2. We have written equation 1 in this format. So this is really equation 1. So comparing equation 1 and equation 2, what do you see? The right hand side is the same. The left hand side alone is different. So the two equations can be equated. That is negative 1 by u plus 1 by v is equal to 1 by f. Or we can write this as 1 by v minus 1 by u is equal to 1 by f. This equation is called thin lens formula. This is also known as law of distances. Law of distances. This equation is applicable for convex lens forming virtual image and also for concave lens. We will just accommodate it here. Let me repeat and make it more clear. Thin lens formula, otherwise called law of distances, is applicable for convex lens forming virtual image and also concave lens. In the derivation, we have really derived it for convex lens forming real image. Okay, I hope it is clear. Due to lack of space, this small portion I have included in these places. Please take care. What does this formula tell us? The formula tells us that for lenses, f depends on the radius of curvature of both surfaces and also the refractive index of the medium of the lens. In the case of spherical mirrors, we have seen that 2f is equal to r. That is the radius of curvature which we mark here as c. So for the case of lenses, c is not always equal to 2f. You have to remember this when you draw diagrams. In doing this derivation, we have used the new Cartesian sign convention. What does it tell us? Distances are always measured from the pole. If the measurement is in the direction of the incident light, such values are taken as positive, and if it is against the direction of incident light, it is taken as negative. For convex lens, f is always taken as positive. We have taken here positive. It has come the right way. F is positive here. And for concave, f is negative. We also have taken certain assumptions. First assumption is that thin lens is used. Then small aperture. Then object is point object, and angle of incidence and angle of refraction are small. I and R are small. So actually there are four assumptions taken. One is lens is thin. Second is the aperture is very small. Third one is object is point object. And fourth one is I and R, the angle of incidence and angle of refraction, are small. I hope this video was clear to you. Okay, we will do the next topic in the next video. Thank you very much.